Okay, this is problem 5-14. My strategy here is just to work a bunch of these for you and increase in difficulty or increase in the concepts you need to understand as by way of review, essentially. Okay, let's draw the beam up here, and I'll just draw my shear and moment diagrams below it. Let's see, we've got a force here. These are two reactions. There's a force of 500 newtons. Here at 200 millimeters, let me switch to meters, so 0.2 meters. At 0.35 meters, there is another load, 600 newtons, and then we move over another 0.25 meters to the reaction, and then 0.4 meters beyond, there's a positive 300 newton load. Okay? All right, let's calculate the reactions first. We may actually need our calculators this time. Let's see, so let's call this A, call this B, and we can work down here and then erase, I guess. So if we sum moments about A so we can get the reaction of B, we'll take this way as positive as usual, counterclockwise as positive. So let's see, we have negative 0.2 times 500. Notice this would be just meters times newton, so it's newton meters of torque. And it's a negative moment. Minus, let's see, 0.2 and 0.35 are 0.55. There's the force at that point. And then let's see, 0.25 and 0.35 would be 0.6 plus 0.2 would be plus 0.8 times the reaction at B for the positive moment. And then we have another positive moment over here from the 300 newton force. So that would be 1.2 multiplied by 300. Anyway, all that sums up to 0. Solving for RB multiplied by 0.8, in fact. We're going to move the other terms to the other side of the equation. As I do it, I'll simplify them. So 20% of 500 would be 100, right? So switch the sign, 100. I hope that's not too fast. I'll make arrows so you can see. 55% of 600, probably could do that, but I'd probably make a mistake, so let's just do it the easy way. It's 330. So there's that term. And this one, 1.2 of 300, let's see, 20% would be 60. I think it's 360, right? Yeah, 360. So minus 360. Do you see why I flipped the signs? All I did was move them to the opposite side of the equation. So far, so good? All right. So let's see. Then if we want RB, then we better sum these and divide by 0.8. So let's see. 100, that's 430 less 360 divided by 0.8. I got 87.5. So the reaction at B should be 87.5 newtons. Okay? Does that seem correct? Seems okay to me. Can I erase this? Give me one more second. One more second. All right. Tell you what, let me just move down in some moments. B. Sum should be 0 because the beam's not rotating. So if I'm summing moments here, well, let's see, we'd have a positive moment of 0.4 times 300. Okay, so that takes care of the moment from that force. Both of these provide a positive moment, so plus 0.25 times 600 plus 0.35 and 0.25 are again 0.6 multiplied by 500. And then finally, the negative moment from A is going to be what? 0.2 plus these, which is 0.8. So minus, let's put that on the next line for the sake of the video, minus 0.8 multiplied by the reaction at A. Okay? Now, rather than rearrange this, since it's getting so low, what I'm going to do is just add all of these together and divide by 0.8. Okay? That should solve for the reaction at A. So let's see, 40% of 300 plus a quarter of 600 plus 60% of 500 divided by 0.8. Looks like the reaction at A is, I'll just write it in up here, 712.5. Okay. Now, let's sum all of this and see if it makes sense. 87.5 plus 712.5 will give us 800, plus 300 is 1100, and sure enough, 500 and 600 are 1100. So the sum of forces verifies that we did this right. Okay? Either that or we made a lot of mistakes somewhere. But I think this is right. So there's our forces. Okay? Next thing, the shear diagram. I can move that down a little bit, I think. Again, the key to figuring out whether something's positive or negative is to think of cutting the beam and then imagining whether the shear has to go down or up. If it has to go down, then it's positive. In fact, it does have to go up. Or I'm sorry, it does have, the shear, the force has to point downward. So that means we have to go to the positive side of the shear axis, and we would go to 712.5 initially. That would remain constant until we get to the 500 Newton load. Okay. So basically the 500 Newton load means that the shear after that section, we won't need all 712, right? Because the 500 is helping to fight the 712. All we need is 212. It's still a downward shear, but now it's only 212.5. Okay? Come on over to the 600 load. What happens there? Well, that's just going to take us below the axis, whatever 212 from 600 is, well, 212.5, so that'd be what, 387.5? Try to draw it to scale the best I can. So there we go, 387.5. Come over to the 87.5 load. That should take us up to 300. I'll tell you what, let's do it this way. Negative 387.5. This is negative 300. And that will go all the way over here, and now the negative 3, or the positive 300 takes us back. So that makes sense. So basically, if we were to cut the beam in this section, what this says, since it's negative, is that the shear would have to be upward, which makes sense because finally the load at the end relieves the shear. Okay? So far, so good? Too fast, too slow? Okay. All right, let's get the moment. The moments would now be in Newton meters because I changed my distances to meters. I did not use the millimeters that were given. Okay. To calculate the magnitude of the moment, all we need to do is calculate some areas. So 712.5 times 20% will be where the moment ends up, at least for the first section up to the first load. So that magnitude, let's see, would be 71.25 times 2 is about 140. I better use my calculator. 142.5, thanks. 142.5 Newton meters. Then we're going to add to that the area from this section, which is 0.35 multiplied by 212.5. 212.5 times 0.35. So this area here is 74.375. Everybody got that? Okay, you can follow along with the calculator if you want. We have to add that to the 142.5. And so we should end up, I need some more space. We should end up, let's see, at a point above, but of course the slope's not as high because we're not adding area as quickly. But this comes out to 216.9. Let me just round it off there if that's okay. It's 875 if you really want to know. Okay, so, and I'll keep it in my calculator so that I can get a decent answer at the end. So then we have negative area, which means that the line's going to come down. So 0.25 times 387.5 away from this 216.875 is how much? Okay, so minus 387.5 times 0.25. How much did you guys get?
120.
120, that's what I got also. You know what, rather than pulling lines off here, let me just write the number above the point. Okay, and then we've got more negative area, 300 times 0.4, so subtract 40% of 300, I get 0, good. Now let's see, this line slope would not be as extreme as this one, right? We're subtracting area faster here than we are here as we move along. Okay? So where's the maximum moment and the maximum shear in this beam? Well, the maximum shear is over in this section. The maximum moment is right there. Where would the beam break? Right there. Wherever the maximum moment is, more likely. And again, shear usually does not cause failure. It's moments that cause failure. Now, at this point, there's also shear to be considered. Now, it can be a little bit confusing because which value of shear would you use? Good question. Well, on this side, you use this value of shear. On this side, you use the other value of shear. Okay. Questions, comments? Yes?
Why is that the max shear?
This is not the max shear, it's the max moment. Did I say max shear? I'm sorry, the max shear is over here at 712.5. It's in this area. My statement was, though, that both the moment and the shear will cause stress in this area of the beam. It's different on the right side than on the left. Anything else?